Complexity, University of Warwick. And the title is Textures and Topology in Rich Crystals.
Okay, thanks, Oleg. I'd like to thank the organizers for inviting me to come. It's a real pleasure to be able to talk to you today and tell you about some work that we've been doing for a while. First, while I was a postdoc with Randy at Penn, more recently, now that I've been at Warwick, on applications of topology to understanding textures in liquid crystals. So I think working in this area, we're really blessed with an abundance of very pretty pictures to look at and try to understand what's going on in them. And we've already heard a number of beautiful talks this morning from Maurice and from Randy on the sorts of things that are going on in these textures and the beautiful structure and mathematics that lies behind trying to understand them. So these are some of my favorites. Apologies if your own personal favorite is not on the display. These are mine. These are all textures that I have done some kind of work with at some time or another. And I think the thing I really want to emphasize about these is that in contrast to the sort of pristine images that you get in textbooks of what ordered phases are, where everything is perfect and you have uniform alignment in the nematic or perfect layers in the smectic, these are all characterized predominantly by the fact that they have defects in them, something that we've heard quite a lot about already today. And in fact, so much so that our original understanding of what these mesophases is, what the type of order in them is, came from an understanding of the defects rather than an understanding of the pristine order that you hear about in textbooks. So if you want to understand textures of liquid crystals, or if you want to understand properties of mesophases generally, then it is essential to study and know something about the defects in the system and how they control the textures that you see. But in addition, you can turn that around, and people have been doing this a lot in recent years, and take the point of view that if you understand something about the defects that arise in mesophases, and you can control them in some way, then you might be able to generate new textures that you don't see every day in the laboratory, new things that are fun and exciting to play with. So again, here is just a selection of things, some a few years old and others bang up to date. This one's still a preprint. So things like emulsions, where you form chains of droplets, or colloidal particles that you can aggregate into different types of lattices. One of my favorites, the nice recent work from the Ljubljana group, where you can rearrange the defect lines around these particles, tie them into all sorts of knots. I'll try and tell you a little bit about that towards the end of my talk. But first of all, I want to say something about how do we go about describing things that are really rather complicated like this. This is some kind of complicated three-dimensional configuration of molecular orientations in space. And it's a real challenge both to think about that in a theoretical way, like somebody like myself would, but also to visualize these things experimentally. It's very difficult just looking at the pictures, for instance this one, to get a clear indication of exactly what direction the molecules are pointing in at every point in space. Okay? So we'd like to have some powerful tools for identifying and characterizing the order in complicated textures like this, and that's the first thing I'd like to try and tell you about. So let's imagine an ideal situation to start with where you have a perfect characterization of the order in the system if you know the positions and the orientations of every molecule in the material, right? So you know the positions and orientations of every molecule. So surely that gives you complete information of the texture. But the first problem that you face is whether or not this is helpful. So here are the positions and orientations of every molecule in some complex textures. And although it's kind of dangerous to do it, I'm tempted to ask the experts in the audience if they have any idea what either of these things are. Right? So I think we can agree that this type of thing, just plotting all of the information all at once, is not a very helpful way of characterizing the order in textures.
They're not saying it's working.
Are they? But they haven't worked it out yet.
They solved it. Apparently they solved it.
I see. Okay.
And I say they can thwart topological defects.
I see. Very good. Okay, so one thing that you might do instead of just showing all of the molecules, is you might show instead where the defects are, right? So you show where there's no orientation in the system. And if we try that, then you see that this helps a lot, at least in some cases. So the experts in the audience, and presumably everybody following Junichi's nice talk before lunch, will recognize that this box of dense sticks is actually blue phase 1. Okay, so this is the structure of blue phase 1. But it's not always a useful thing to do. Apparently the one on the right has no defects. Does that mean it's just a boring uniform texture? Who thinks it's a boring uniform texture? Randy, what do you think it is? Okay. So another thing you might do, instead of plotting all of the orientations or none of the orientations, you might take slices and have a look slice by slice and see if you can get a feel for what's going on. And these are all good techniques, but they don't always work, and it still requires a little bit of effort and expertise and experience in order to figure out what's going on. For instance, I'm not entirely sure that this image helps you very much to identify this texture. So we're looking for some kind of general, powerful tool that might help us in visualizing, characterizing, and ultimately manipulating complicated three-dimensional textures. So I want to try and tell you in rough outline how some standard topological techniques developed by Lev Pontryagin and René Thom in the middle half of the last century can shed some insight into these kinds of problems. It turns out that the thing that you should do is something that we've been doing in liquid crystals for a long time. You should take an image that looks like this. This is a classic Schlieren texture, or more correctly, this is the right thing to do for thin films or for two-dimensional problems. And I'll tell you about it first, and then we'll see how everything generalizes nicely to the three-dimensional setting. All right, so this is a Schlieren texture. I'm sure everyone in the room has seen this kind of thing a million times before, but let me run through briefly what it is and what it tells us about the order in the texture. So here's my theorist's cartoon. Apologies to the experimentalists for dumbing this down so much. This is my theorist's cartoon for how you take these pictures. You get a light source. You shine it at some cell of material. The cell has cross polarizers across it. So if there's no stuff in between, then there's no light comes through. It's dark. But instead, you put a liquid crystal in between, and the molecules point at some direction relative to the polarizer and analyzer. They rotate the plane of polarization, and you see some bright light. That works as long as the molecules are pointing at some angle relative to the polarizer and analyzer. So if they're pointing either exactly parallel to the polarizer or exactly parallel to the analyzer, they don't rotate the plane of polarization, and it's dark. So the reason you have all these dark brushes is because that's where the molecules are pointing in one of these two directions. All right? So if I give you some textures now, you can draw the corresponding patterns fairly easily. You just look everywhere where the molecules are aligned either up-down or left-right, and you draw a brush on it, and you get these patterns. Look exactly like you see in the Schlieren texture, right? So if you have a texture, you can construct a pattern of brushes fairly easily. And if you have a pattern of brushes, then you know what direction the molecules point in along those lines, and you can reconstruct information about the texture. Let me go through this in a little more detail with a blow-up of this, of a part of this image from the Schlieren texture. So like I said, these lines are places where the orientations are either up, down, or left, right. And it turns out that the pattern of these brushes conveys all of the information about the system, all of the topological information. So you know, for instance, that say along this line, the orientation is left, right, and then along this line, it must be up, down. And the points where the brushes meet are the defects. And you have this standard story that if there are 4 brushes that meet, that's strength plus or minus 1. And if you have these other locations where there are only 2 brushes that meet, that's strength plus or minus 1/2. Okay? So it suffices for extracting the topological information in the system to look at only one of these directions. Turns out there's enough information just in one of them. So we pick one of them, like say for instance the analyzer direction, and we're going to keep those brushes and the locations of the defects and get rid of everything else. But before we do that, there's one extra piece of information we need to keep, and that is if I have 4 brushes, that tells me that the defect is strength plus or minus 1, and it doesn't tell me the sign, right? To get the sign, you know how I get the sign? I rotate the polarizers and I see whether the brush pattern rotates in the same direction or the opposite direction. It tells me whether it's plus or minus 1. So I'm going to encode that information by putting little arrows on the brushes. It's like electric field lines. If they're pointing away from the defect, that's positive, and if they're pointing towards the defect, that's negative. So look, we can understand everything, right? This is a +1 defect. It has 2 brushes that have arrows pointing out, and this is a -1/2. There's 1 arrow that's pointing in. Okay, so we can understand everything about texture in this way. All right, and then you can get rid of everything that's in the background, and the topological information about this texture is entirely contained in a picture of this kind, where you show the locations of the defects and where the molecules are pointing left, right, where they're in the analyzer direction, decorated with arrows to tell you the signs of the defects. All right, so this is a complete topological characterization of the texture in a reduced form where you can really see everything. Right? So it's not going to be some dense forest of sticks when I show you the 3D pictures. What's important about this is that it's a two-way process. You get to start with a texture and turn it into some pattern of lines like this, but you also get to go backwards. So suppose I start with this picture and I send it to Brian, and he has no idea that it came from some Schlieren texture, and I ask him to reconstruct what's going on. He's supposed to be able to start with this picture and put back the director field everywhere. But that's relatively straightforward because we know the rules that went into making this, and so we can just reverse the process. You know, for instance, that everywhere along these lines, the orientation is just horizontal, just along the analyzer direction. And also because you have these arrows telling you the local behavior in the vicinity of each of the lines. Locally, this is like a -1/2. This is like a +1/2. Then you can also put in local textural information around the brushes and in the vicinity of each of the defects. So you start to build up a reconstruction, at least locally, of what the texture looks like. And with this in place, then you can do some slightly more global reconstruction. Say, for instance, try and put back all of the polarizer brushes. Right? I got rid of half of the brushes in my original picture. Now I can put them back because I've reconstructed locally what the texture looks like, and I can join the lines back up again. Okay, so that's a complete reconstruction of the texture starting from this set of lines that carries all the topological information. And then you can check and see how well I did, and it's not bad. Okay, it's not perfect, but it's not bad. Up to continuous deformations, you reconstruct the texture correctly. All right, so that's the idea for two-dimensional textures. What's going on? What about in 3 dimensions? How does the story generalize? So the idea in 3 dimensions is to do something similar. We're going to plot some subset of orientations in the system. And in particular, the construction goes this way. So fix some, usually these textures that we get, that we deal with, they're in some kind of cell that has boundary conditions on them. So for instance, uniform boundary conditions, everything's going to be pointing straight up at large distances. So you take that as a special direction. And if everything throughout the entire cell is just pointing straight up, that's kind of boring. That's a simple or kind of trivial texture. So we're interested in when the orientation is not up-down, when the orientation is along the analyzer direction, the left-right direction. So we should look everywhere in the material where the orientation is not up-down. That's going to be a horizontal direction. And the only difference in 3 dimensions is that there's more than one horizontal direction, right? You have an entire family of them that are horizontal instead of up-down. So instead of just plotting a single polarizer direction, I'm going to plot everything that is horizontal. So that's an entire family of directions. It's going to give me, instead of a set of brushes, some kind of surface in my texture. And then there's more information in it because horizontal means both this way and that direction and the other direction. And I'd like to distinguish between these. So I'm going to color them as indicated on the strip. This direction is going to be red, and this direction towards you is going to be green, and over here is going to be blue. And by the time I get this way, that's the same as I started with, right? Because it's a pneumatic, so this way is the same as that way. It better be red again. Okay? So there'll be 2 full cycles, red, green, blue, red, green, blue, red, to get a full 2 pi rotation. Okay? That's just a pneumatic thing. So let's have a look and see how it works out. Here's some complicated texture again. I plot the positions and orientations of all the molecules. It's not very helpful. And then I take all of the directions that are horizontal. I get some kind of smooth surface instead. So that's already an improvement. It's somewhat easier to see. And I get to color it according to the orientation within the horizontal plane. So everything that's horizontal and pointing this way is red. Everything that's horizontal and pointing this way is green, and this way is blue. Okay? So you get some characterization of what the texture looks like in this way.
Where would that texture take from? I mean, did you construct that texture?
This particular one is a little short simulation, and I'll show you exactly what it is in a couple of slides' time. Right? There's also an experiment to go with it. Okay, so to understand what the texture is, or before I come on to telling you exactly what the texture is, some of the experts will know already. Let me give you 1 or 2 more bits of information about how to interpret these pictures. So what I want to show here is what the defects look like in terms of these colored surfaces. So the defects in a Schlieren texture are places where either the brushes end, they end on a point defect, and then there's no additional brush going further on, or places where the arrows reverse sign. All right? And it's a similar sort of story here. So they're either boundaries to the pre-images that you construct, or they're singular points in the decoration that you add on top of the pre-image surface that you construct. And that's true for defects in 3 dimensions. We have 2 types of defects. There are line defects, and those are boundaries to the surface. You have some part of the surface that comes along, it has some color on it. In this case, it's uniform color. That means everywhere the orientation is, say, in this direction, and then it just stops. So what's going on in this thing? Well, this is a classic disclination line. It's on this side, on the colored part of the cell. Everything is horizontal and pointing this direction. And then I come over in this direction, and the orientation points up vertically. And then if I try to come underneath, it's going to continue rotating around and be pointing the opposite direction on the underside of the sheet. Okay? So that's what it looks like in terms of these surfaces. And if you know how the surfaces are constructed, then you can reproduce the texture everywhere, at least up to some continuous deformation. So those are disclination lines. They're boundaries to the surface. And point defects correspond to singularities in the color winding. Right? This is all the orientations are in the plane, and you're going red, green, blue, red, green, blue, red. So that's red was this way. You swing around green, blue, red, and keep going around green, blue, red. That's a full 2 pi rotation in the horizontal orientations, and that's the characteristic hallmark of a point defect. So the different types of point defects, we heard from Maurice this morning, that they're characterized by pi 2 of RP2, which is the integers, and that corresponds to the different types of windings that you can have going around the color wheel. So there's an exact correspondence here. Okay, so with that information, what can we say about this example that I showed you previously and try to identify what the texture is? Well, the first thing to say about it is that this is a smooth surface without boundary. So there are no boundaries, there are no disclination lines in this texture. Right? This has no disclination lines anywhere. But there is color winding on it. And if you think about what's happening as you go towards the 2 poles, all of the colors are coming together and spiraling around each other in this characteristic fashion that identifies the existence of a point defect. So here I have some texture where there are 2 point defects, one at the top of the cell, one at the bottom of the cell, and everywhere else there are no singularities, no disclination lines. And then if you look at what's happening around the equatorial region, you have at the far end, it's red, and as I go in any direction away from red, say along the radial direction, I'm horizontal, and as I move away from the surface, I'm not horizontal. So I'm doing some kind of rotation as I go radially outwards. And also, as I go up, down, as I go up, I'm turning into green, and as I go down, I'm turning into blue. So going in the up-down direction again is also a rotation in the direction of the director field. And so locally around this central region, you have an area of double twist. So this is some kind of torus of double twist with two defects, one above and below. That's the classic hallmark of these beautiful things that Ivan discovered a number of years ago in his lab called torons. Okay, so you get to reconstruct fun textures of this kind and understand complicated textures of this kind in some remarkable detail with these type of techniques.
So the point defects, those are hedgehogs?
That's right. Exactly. One above, one below. What's particularly nice about this is that in addition to the sort of silly little pictures and simulations that I run, you can take real data and reconstruct actual director fields from real experimental data and analyze the textures using the same techniques. So I want to show you some things that we did on that in collaboration with Ivan and Paul Ackerman at CU Boulder. So the idea here is to image in slices through the vertical depth of the material and get a stack of intensity images for the scattered light from different depths in the sample. So that's what you're seeing here. You're seeing a scan vertically through the material at the intensity at different levels. And then you take a family of these images corresponding to different linear polarizations. You take a linear polarization, say that's going this way, and a linear polarization is going that way, the one that's at the two that are 45 degrees. And if you take this and combine them together using Stokes parameters from the intensity data, you can back out what the actual polarization state of the light was. And if you think that the scattered light is scattered because of the local orientation in the liquid crystal, then what that polarization state of the light that's coming off is telling you is what the orientation of the liquid crystals in this particular slice of the material was. So you get to reconstruct the director field in the material by taking some combination of linear polarization images and reconstructing using Stokes parameters. So now we have the positions and orientations of all of the molecules in the box. We could plot some kind of complicated dense forest of sticks, or we could try to simplify the picture and show one of these colored surfaces. So here's the reconstruction. Here's some snapshots through different levels of the height. This is the sketch for the structure of the toron. You see the double twist cylinder, or the double twist ring, and the 2 point defects, top and below. And this is the reconstruction from the experimental data. Okay.
So when you have a three-dimensional structure, the scattering doesn't have to be done over the whole path that goes through? How do I think about it?
Right. So there are a number of techniques. And Ivan will correct me if I say something terribly wrong. You can do confocal slicing so as to get just from a single region. What's done here, I believe, is a 3-photon process. So it's a strongly nonlinear process, and then it's dependent on the intensity. So it's the signal is coming predominantly from where the intensity in the laser beam is large, and effectively that's a slice in the material. Okay, I hope I said that. Right. Okay, so what can you do with this? Well, here's an interesting question that you can do with this to generate some kind of new structure that's interesting and identify it topologically. So this thing is produced from a frustrated cholesteric cell. It's a thin cell. The thickness is comparable to the pitch in the cholesteric. And initially, everything just points vertically upwards. And then the non-trivial texture, this one, is induced locally by shining a laser beam on the sample. But initially, it starts, there are no defects in the system whatsoever. Then you produce this structure. This structure has only 2 hedgehogs in it. It came from something that was uniform. It must be possible to take those two defects, combine them together, and get rid of them so that you have a defect-free texture. All right? So what happens if we try to do that? Okay. What do you think? You go back to just a uniform texture, or do you get something interesting? So here again, experimental data for what happens if you perturb the system. It can be done in one of two ways, either by starting with a toron and massaging it with a focused laser beam to try and persuade the two defects to annihilate against each other. Then you form an interesting new texture, looks like has this appearance. Or you can nucleate this directly by shining the laser beam on the aligned sample and moving the focus of the laser beam in a small circle. So this texture is characterized by having no defects, and yet it's not a trivial texture. This is not a texture that is equivalent to the state that you started with, where everything was just pointing uniformly straight up. And you can tell that it's a non-trivial texture because the various color circles on this object are all linked with each other. They're all linked rings. Okay? So if you look at this, the green circle that goes around here goes underneath the torus and back up again. That links with the blue circle, and it links with the red circle and the other green circle, and so on and so forth. So what I have here is this intricate pattern where all of the colors are interlinked with each other. They're all linked rings with linking number 1. All right? And there's no way to undo that, because in order to do that, I would have to have two of the colors pass through each other to be unlinked. And if two of the colors are at the same point in space, then at that point in space, the director is trying to point both in this direction and that direction. That corresponds to a defect. So there's no continuous deformation that will get rid of this thing. Okay. Of course, what this thing is...
Didn't you get from there by continuous deformation of the structure with 2-point defects?
Yes.
And can't you...
Exactly, with 2-point defects. I generated defects to get here. There's nothing that's continuous that does not involve the formation of defects. Right? That's the point. I can undo it, but undoing it means you take these two linked circles and you unlink them. And in the process of unlinking, two of the colors will coincide at a single point in space. And that means at that point in space, it's both pointing this way, and that's a disclination, or a hedgehog.
When you went from the original structure with 2 hedgehogs to this, was that continuous?
Well, that involves annihilating the two defects. So if you think that, taking a texture where there are 2 defects and ending with a texture where there are none, then the process where they actually annihilate is changing the number of defects in the system.
But there's not necessarily there's not actually a barrier there.
No, absolutely. I mean, this is an experiment, right? They make the transition.
What you're saying seems to indicate that there's some topological rules that some topological quantity is conserved and you can't change. Is that so? I mean, the fact that you cannot, by smooth deformation, get rid of it.
Yes. Yes, I understand perfectly. Yes, that's the next slide. Okay, so this was also something that was discussed this morning by Maurice, so I don't need to say too much about it. The texture that you're seeing here that is characterized by this beautiful structure, by this interlinking of pre-images of particular directions, is a famous texture in mathematics known as the Haupt vibration. So here's a beautiful example of how you can construct the Haupt vibration experimentally in liquid crystals and generate some kind of interesting new texture. Okay, so I'd like to press on. So that was one story I wanted to tell you. Sorry.
Projection of vibration.
Exactly, yes, absolutely. We're in R3, so stereographic projection done. The linking number, right? The linking number is +1, +2, -5.
Sorry, I hope this is not an assault, but just a lot of interest. But a linking number would indicate that you cannot break things, but it's a sort of liquid crystal director. Can't you just let them go one through the other like this?
Okay.
Zero energy cost.
So no, not zero energy cost. That's what I said previously. Right, what does it mean for the two rings to pass through each other? Well, at some stage, you're going to have red and green at exactly the same point in space. And red means you want to point this direction, and green means you want to point that direction. So that's a defect in the orientational order.
That would be the nucleation.
Right. Okay?
So is it the case that, I mean, there's an infinite number of these rings, right? And you're saying every one of them is exactly the same linking number with every other one. and that
Exactly.
number is 1.
Exactly.
Are there more Baroque possibilities where different rings can have different linking numbers with different other rings, or is there some
No.
thing?
There aren't.
Okay.
They're all definite linking number.
But no, I mean, they're all definite linking numbers. Do they all have to be the same?
Yes.
Oh, okay.
Yes. Every direction is the same as every
Is
other
that supposed to
direction.
be obvious to me, or is that some deep theory?
Yes.
Thanks, Randy. I'll take that answer. Okay.
Okay, that's impossible.
Okay. So that was one thing I wanted to tell you about applications of topology to understanding textures in liquid crystals. Now I want to tell you a slightly different one, or something that, at least to begin with, will be a slightly different one. I want to tell you some fun work that we've been doing for the past couple of years in Warwick, thinking about controlling textures with colloids. So this is a popular endeavor over the past sort of 10 or 15 years or so, because colloidal particles, the idea is that you have these small particles and you coat them with boundary conditions such that the director wants to point everywhere radially away from the surface, and that looks like a +1 point defect. So if you put these into a liquid crystal, they look like defects. And as I said at the outset, textures in liquid crystals are dominated by what the defects are doing. And the idea here is to put in the defects that you want and to manipulate them and control them and put them where you want them to be, and then they'll generate naturally interesting textures for you. So what we're doing here is putting interesting surfaces with normal boundary conditions into a liquid crystal and using it to control the sorts of textures that you can get. So some of the fun things that you can get, this was done by my friend Miha a number of years ago, is with pairs of particles you can get interesting entangled states where single disclination lines will go around multiple colloids and generate ostensibly new configurations and topological structures in liquid crystals. And then some of the more recent, really interesting things that people can do. I already mentioned at the outset that if you have a bunch of colloids and you come along with a laser tweezer and persuade with enough skill the defect lines to reconnect with each other in the appropriate way around this assembly of colloids, you can tie them into a whole slew of different knots and links, which seems like a lot of fun to me. And then very recently, this past year, coming out of Ivan's group, there's been fabrication of colloidal particles that are not just spheres, but are tori or multiple hole tori, higher genus surfaces of various kinds. And you can study how the topology of the particle that you're putting into the liquid crystal interacts with the type of defects that you form. So we got excited by this and wanted to know whether we could construct any knots of our own and whether we could do it just by choosing the right topological properties for the colloid that you throw into the liquid crystal. So the first question that you should ask yourself there is, what are the topological implications of putting different types of surfaces into a liquid crystal? So that's what I want to tell you about first. So all of the surfaces that I'm going to talk about have homeotropic boundary conditions. The liquid crystal wants to point along the surface normal direction everywhere. So the point of this slide is twofold. It's to summarize the influence of each of these types of surfaces for the liquid crystal, and also to point out that the things that people have been playing with so far, things like spheres or tori, even tori of arbitrary genus, those are all surfaces of a particular type, and there's more than one type of surface. In fact, there are sort of 4 different classes of surfaces that you might think of, depending on whether the surface is closed or has a boundary to it, and depending on whether the surface is orientable or non-orientable. Right? So closed with boundary, those are things like spheres and tori. Closed and orientable. Orientable with boundary, things like a disk or a torus that you've cut a hole out of. non-orientable, something like a Klein bottle, and non-orientable with boundaries, something like a Mobius strip. Okay. So what I want to do is run through the implications of these things for generating defects in liquid crystals, at least the implications from a purely topological point of view. And those are twofold. One, you get point defects in the liquid crystal associated with closed orientable surfaces, and you get line defects necessarily associated with any surface that is non-orientable and has a boundary. Okay, so here are the closed orientable surfaces. These ones, like I just said, generate point defects. Now, if you look at the images, you'll see that there are both point defects. Here's a point defect at the center of the structure. And then around the outside, it's surrounded by a line defect. Right? And I said these always generate point defects, and yet here's a line defect. That's an energetic thing. Okay, that's just an energetic behavior. It's known that point defects can open up into little disclination loops, or disclination loops can shrink into points. And that's the case for all of the defects in these systems. In fact, you can see that process. It's a beautiful image because you can see it directly. Here's a point defect, and here's a point defect that's opened up into a loop, right? And they're just a continuous transformation from one to the other. So in all of these cases, whether what you're seeing is actually a point or is actually a line, from a topological point of view, they may as well all be points. And so the topological content of closed orientable surfaces is that they generate point defects, and you should ask yourself, how many point defects do they generate? And they generate this many. They generate 1 minus whatever the number of holes in the surface is. Okay. The second thing is, what happens if you have an orientable surface, but you cut a hole in it? So here's a sphere, I lopped part of it off, part of the northern hemisphere off. Or here's a torus, I cut a little hole in it. And here, these are completely boring from a topological point of view. They don't generate any defects at all. And one way of thinking about this is to think about the difference between a colloid in a surrounding liquid crystal, which generates a point defect, and a spherical droplet of liquid crystal, which also generates a defect, but in the interior. And that's a generic property of closed orientable surfaces, that if the liquid crystal is outside, they generate a defect, and if the liquid crystal is inside the surface, they also generate a defect. And so if you cut a hole in it, the defect that's inside and the defect that's outside can annihilate against each other. And from a topological point of view, these are totally boring. They don't generate anything.
But as you were saying earlier, energetics can do different things.
Absolutely.
They might want to actually stay apart.
Absolutely.
If the hole is small, they will.
Yes, absolutely. But this is just a topological story so far.
So this inside-outside connection, does it carry over if you consider tangential boundary conditions to the surfaces rather than like it is?
I don't know. I'm telling you the story only for homeotropic boundary conditions.
Because there's no lyrics.
And I don't want to commit
How much time do you have to present?
4 or 5 minutes.
So please hold your questions till there is a
Okay.
time for questions.
Thanks, Ole. All right. The non-orientable closed surfaces are also boring because they don't embed in three-dimensional space, so you can't make them. So we're not going to talk about them. All right. They might be very interesting, but we can't ask Ivan to make them, so they're not so interesting. That leaves non-orientable surfaces with boundary, something like this Mobius strip. And they're interesting because they generate disclination loops for you. They generate disclination loops for the following reason. So suppose I told you this is normal boundary conditions. The molecules are always pointing along the local surface normal. So look at what happens to the local surface normal around this green strip. Okay? Here's what happens to it. It's a non-orientable surface. The surface normal rotates as you go around, and it comes back pointing exactly the other way around. So that type of change, that type of transformation in the director field, where it rotates by pi and going around some closed circuit, is the indicator that somewhere inside this closed circuit, or on any disk that binds the green circuit, there must be a disclination line that's passing through it. So not only do you generate disclination lines, you generate disclination lines that are intrinsically entangled with the colloidal particle. Okay. All right, so here's the classification again. All right, well, that's the principle. Does it actually work? So you can try and make little models of this to run simulations on and see that everything works out as expected. Here's a simulation, finite difference using Landau-Dijen. It's the same free energy as Junichi told us about before lunch. You do finite difference relaxation. Here's the texture. There's the disclination loop. Runs around. Thanks very much. Runs around the colloid exactly as predicted. There's a small subtlety here. It's a technical challenge experimentally to make an actual genuine two-dimensional surface, because most of the things that we make have some kind of thickness to them, unless it's like graphene or something like that. So if it's thickened out by some amount, then you have to worry about what's happening on the thin edge so that you correctly mimic an actual non-orientable surface. And what you need here is a switch from homeotropic boundary conditions to planar anchoring on the thin edge. Okay, and this is a technical challenge, but we have very good experimentalists. I'm sure they'll manage it. Okay. The other thing that's cool about Möbius strips is that you don't have to put just one turn in them. You can put more than one turn into them. This is gorgeous. This is from Möbius's original paper, right? He shows you how to make all these things, just folding strips of paper. What's interesting about these, what I particularly like about them, is if you look at this three-twisted Möbius strip and ask what the boundary of the strip looks like, it's a single closed curve, and it's an interesting single closed curve. It's a trefoil knot, right? So if I have this particle and I throw it into a liquid crystal, and I know it's going to generate a disclination loop that is entangled with the particle, wouldn't it be really neat if it adopted the shape of the boundary of the particle and made a trefoil knot for me? Wouldn't that be really cool? So that's exactly what it does, right? We did it, we coded it up, Tom coded it up, ran the simulations. You get different torus knots. Here's a Hopf-Link trefoil knot. This is Solomon's knot, and this is the Sankofoil. Okay, so you can generate all sorts of gorgeous knotted disclination loops by using colloids with the right topological properties. And I think I'm going to skip this slide and go on to the last one and just say, so here's a reconstruction of the entire texture, not just where the defect is, but also the entire topological content of the texture in these systems using this colored surface approach that I talked about in the first half. So we have, I guess this is a threefold Möbius strip with a trefoil knot around it. Here's my surface. And you'll notice that it has color winding around it that has these singular points associated to it, exactly the same as in the torons. And they're showing the locations of 2 point defects, top and bottom in the system. So this is much the same setup as what is used in the toron work. You have a frustrated cholesteric cell where the thickness is comparable to the pitch, and you nucleate the texture locally, and it has, at least in its global properties away from the disclination line, much the same structure as the toron. In fact, you can think of this disclination loop, this trefoil knot, as being the center line of the double twist cylinder, which is like an escaped strength 1 defect. We heard about this from Maurice this morning, that if you try to make a strength 1 defect in a liquid crystal, it can escape. You can think of the double twist cylinder as that escaped line. And if you split the strength 1, the escaped strength 1, into 2 strength 1/2 lines and wrap them around a particle, then they generate this trefoil knot. So you can think of the global texture in these things as being much the same as what's going on in torons. And with that, I'll put up my acknowledgement slide, and thank you for your attention.
Questions?
Carl.
Good talk, Gareth. It's beautiful. Just wondering on the twisted knot stuff at the very end. Could you generate any knot you want instead of a torus knot by using your favorite secret surface instead of just the Möbius strips?
Yes. If you want to know about things like this, go and talk to Tom at the poster session.
What did you say, the Möbius strip isn't the Cypher surface?
But you can construct a Seifert surface for any knot.
Sure.
So suppose you construct a Seifert surface. So let me back up. Let me retract that statement right away for a rather obvious reason. Seifert surfaces are orientable with boundary. But you could use a checkerboard surface for the knot, which typically is non-orientable, and then hope that that would do the same thing.
Slobodan.
Is this annihilation of these two defects which occur in your Turon
Uh-huh.
Something similar as pushing together two of these dipolar colloidal particles where they have two point defects and they come together, you get the bubblegum structure?
It's
so far?
identical. In fact, I had that comparison in my slides, but I took it out because I thought it would be too long. It's exactly the same thing.
The last question.
So in the case where you have a torus and you have either an isolated discrimination in the middle or a discrimination loop around the equator, and you say that's just energetics. So what's going on exactly? So what are you changing in the system to go from one to the other?
That's a good question. You might be better asking that question to Ivan as to what, because here, I mean, one of the typical things that makes the transition is the thickness of the cell. But here, these are all in a uniform cell. I mean, it's the same color.
Go back to his
The
picture.
stable state is a stable state, so you can generate in the same cell both kinds.
Not same cell, go back here. See, you
Right.
have coexisting. Look at picture B.
This one.
Yeah, so you have, sometimes you have a ring, sometimes you have a point.
So the arrow, so the, I would say is bistable. So in the system is bistable. Okay.
That'll make the display people excited.
Multi-stable.
Okay, I'm sorry, we have to end this presentation and discussion. Gareth, thank you very much.